So this is similar triangles part 2. So I've got the same rules as in my first video on this up on the board. So the corresponding angles being the same, corresponding sides in the same ratio. And if you remember from my last video, I said to you that if you've got similar triangles, then you only need to prove either the angles or the sides, and then the other condition will also be true, and we know that they're similar. Now in this particular situation, we've got we have actually got two triangles, but one is inside the other one, and you'll notice that no angles at all have been labelled on there. So how do we know if they're mathematically similar? And that's the first question. And once you get familiar with this, you'll spot a question like this, and in this case it's asked you to find the length of AD, and it's given you some information here. Once you've seen this a few times, you'll begin to sort of recognise what's going on. Now the key with this is recognising its similar triangles in the first place. So if you look at triangle CDE and ABC, you'll notice that this angle down here appears in both triangles, and so therefore that is one angle that is in both. The other thing we've got going on here is you notice the arrows on these two lines here. Now those arrows mean that the lines are parallel, and if they're parallel, then we can use some of our knowledge of parallel lines and angles in parallel lines. Now if you look carefully, you'll notice that we have an F shape there and an F shape here, which means that this angle and this angle are corresponding angles, and here we have this angle and this angle, which are also corresponding angles. So now we definitely have similar triangles, because we have this triangle here which has got dot, single line, double line, and the bigger triangle here which has got dot, single line, double line. Now sometimes you might wish, and I would recommend this, to actually draw out the two triangles separately so you can see what's going on, and then you can label that information on as well. Now it doesn't have to be the most beautiful diagram in the world, but it is a good idea if you put all of the information on. So this is A, B and C, okay, and I'm going to put on the dot, the single and the double lines, so that I can see my angles that are the same. Now I'm told that AB is 12 centimetres, so I'm going to put that on, and DE doesn't appear on there, neither does DC, so that's all the information I have for that one. This one is a slightly smaller one, so I'm going to make my diagram look a little bit smaller, okay, and this one is DEC, and we have a double line here, single line here and a dot here. Now from the information that we were given here, DE is 9 centimetres and DC is 6 centimetres. Okay, so that's all the information that we have. Now the question says we've got to find the length of AD. Now AD is not actually a length of either of the triangles, but if you look carefully, if we find the length of AC, which is this one here, and we already know DC, we can subtract those two and then we'll have AD. So the key here is looking at what you've got to do, break it down and think about it in stages. So our first step is we need to find, step number one if you like, is we've got to find AC, okay? Now in order to find AC, if you remember from last time, the first thing to do is to find the scale factor, okay? Now our scale factor, in this case, we're going to do, remember, a length on the big side divided by length on the, a length on the big triangle divided by length on the shorter or the smaller triangle. So you've got to find your corresponding sides. Now hopefully you've spotted it. We've got single line, double line, single line, double line between the two angles. So therefore it's 12 and 9. The bigger number is 12, so we put that on the top. Smaller number is 9, so we're going to put that on the bottom. Ooh, it's a fraction, and it's not one that works out to be an exact number, but we can work with it. So we cancel it down. 3 goes into both of those, goes into 12 4 times, and it goes into 9 3 times. And yes, you can still do this without a calculator. Now, if you remember rightly, now we've got our scale factor of 4/3. If I want to go from Now this time that one's the small one, so if I want to go from the small to the big, I'm going to multiply by my 4/3, and if I want to go from big to small, I'm going to divide by 4/3. Okay, so make sure you get the order the right way around. So small to big, so you're getting bigger, you multiply, and if you're going from big to small, you divide. Okay, so now we have our scale factor. We want to find AC. Now that's a length on the bigger triangle. So which is the corresponding side? Well, AC is here, double line to dot, and DC is double line to dot here. So these are our corresponding sides. And if we want to go from the small triangle to the big triangle, we have to multiply. So AC is going to be equal to that length, which is 6, multiplied by our scale factor, which is 4/3. Okay, if this was a non-calculator paper, turn your 6 into a fraction, so it's 6/1, and then follow your rules for multiplying fractions. Cancel first any numerator with any denominator. So in this case we've got the 3 and the 6 that cancel. So 3's go into both, so 3's into 3 is 1, 3's into 6 is 2, and then we just multiply across. 2 times 4 is 8. 1 times 1 is 1. If we get 1 in the denominator, we leave it alone. So AC is 8 centimetres. Now, final step then. We need to find AD. Now to find AD, all we do is a quick subtraction. So AD is equal to the length AC, which is that big length there, take away DC, and AC is 8 and DC is 6, so AD is 2 centimetres, and that is your final answer. Quite nice and straightforward.